Okay, so video number 3 on the properties of liquids, because what video 2 talked about was really the basics of liquids and, the difference between evaporation and boiling point. But now we're looking more at the specific properties of liquids. And one of the most important properties of liquids is viscosity. Viscosity is something you may have heard of. They talk about it with things like oil, like motor oil a lot. And it is defined as the resistance to flow. It's basically how thick a liquid is. Think of a milkshake, and we would say, oh, a milkshake's really thick. What we really mean is it has a high viscosity. And so this picture here, this is really high viscosity. Notice that it's not flowing very well. This would be something with quite low viscosity, something that does flow well. Okay? And why is it that this liquid over here, whatever it is, has a high viscosity and this guy has a low? Well, you can imagine the particles in that liquid would have to be moving by each other in order to flow. So if the particles need to move by each other, then attractive forces are going to come into play here. And the deal is the larger attractive forces have higher viscosity. So larger attractive forces equal higher viscosity. If the particles are really attracted to each other, they are not going to be able to flow past each other very well, and the liquid is going to seem very thick. If you look at this table right here, this is the viscosity of a series of hydrocarbons. Hydrocarbon, we know a compound that contains hydrogen and carbon. And if you look at this is the lowest viscosity and this is the highest. Right? A lot of students get that confused because it's in scientific notation, right? But 1.42 times 10 to the negative 3 is larger than those other numbers. And if I look at them and look at the molecules, they are all non-polar. How do I know? Well, they contain only hydrogen and carbon, and that's a non-polar bond. And if you have a nonpolar bond, if the whole molecule is made up of just nonpolar bonds, you can't have a polar molecule. So unless there's lone pairs in it, I guess I should say. There's no lone pairs in here. So what is making the difference? Well, since they're all nonpolar, that means that all they have are London dispersion forces. And maybe video 1, we learned that the larger the London dispersion, I shouldn't say the larger the London dispersion force, the larger the molecule, the more electrons the molecule has, the more polarizable it is, and therefore it will have larger London dispersion forces. So see how decane is the largest molecule here? It has the most electrons, which means it is the most polarizable. Right? Because remember, London dispersion forces are all about the random placement of electrons, so that at any one time, the electrons could be on one side of the molecule. Since it's the most polarizable, it has the largest London dispersion forces. Therefore, it has the highest viscosity. Right, this would be a great place or a great example of a CER that I could ask, give you a couple different molecules and say, which one do you think would have the highest viscosity? Explain your reasoning, right? And so you would have to, go and think about what are the attractive forces between those molecules. The second one is temperature, and this makes a lot of sense because, it's all about attractive forces, but we know at a higher temperature, those molecules can overcome those attractive forces. So at a higher temperature, you have a lower viscosity. There is less of a resistance to flow. And that means, or what happens? Well, if there's higher temperature, that means those particles have more kinetic energy or more energy, and they're able to overcome or partially overcome the forces that are holding it together. Usually they could be intermolecular forces or any other forces holding it together. A great example of this is lava. If you've ever seen like a volcano exploding, you can see that the lava, when it's red hot, it flows and it looks almost like water. Remember, lava is rock, right? So you have liquid rock, molten rock, and because it is so hot, those particles have tons of energy and they're able to overcome the forces that would normally hold all those minerals together. And then as lava cools, it becomes less red, more black, and it moves slowly. Okay? Another property of liquids is surface tension. Surface tension, or how have you ever heard of it? You may have seen, this is when you look at like a freshly waxed car and you can see the water kind of bubbles up on the car. It looks like little pools of water. Or if you've ever done the experiment where you've taken drops of water on a penny, right, and seen how many drops of water can fit on that penny. Or like a bug walking on the water. That's an example of surface tension. So what is the definition of surface tension? It's kind of wordy. I'm going to say it first and then I'll write it. The intermolecular cohesive attraction that causes a liquid to minimize its surface area. So the intermolecular cohesive attraction Now, what the heck does that mean? So intermolecular, right, means between molecules, and then attraction. So this is the attraction between molecules, okay? The intermolecular cohesive attraction, that causes a liquid to minimize its surface area. A liquid to minimize its surface area. Right? Look at this picture over here. Right? The cohesive forces. So these are the forces between molecules. That's what these arrows are showing here. And they're attractive forces. And they are pulling the particles together so that it minimizes surface area, so that there's the least amount of particles on the edge. That's what it wants, is the least amount of particles on the edge. You can imagine if this was flatter, right? There would be more particles on the edge. If a particle is in the middle, it's more attracted to other particles. So that's what it wants. And then here's really that word cohesion, right? The word cohesion is the force of attraction between two of the same molecules, right? Here's the little guys. What color do we want for this? The same molecules. And then adhesion is two different molecules. So both of these start out with the force of attraction between. And then a cohesive force is the two of the same molecule, and an adhesive force is different molecules, right? Because we don't always have to have a sample of pure water, but then also if we have water in something, there are forces that are going on with the water and the container that it's in. So this picture here shows two different test tubes. And the test tube on the left, these are both glass test tubes, and the test tube on the left is water, right? And we know water is very polar, and water is very attractive, or attracted, I should say, is very attracted to the glass. And so it's adhesive forces. So think of the adhesive as being water to glass, is greater than the cohesive, which is water to water, the water molecules sort of climb up the sides of the container. And I'm just going to over exaggerate this here. That's how you get a meniscus, right? We call that a meniscus. But if I take the same glass test tube, but I put mercury in it, right? Mercury is very non-polar. And here is the mercury glass adhesive forces. And here's the mercury cohesive forces. And this is the exact opposite scenario. Cohesive is greater than adhesive. The mercury molecules, we shouldn't say mercury molecules. We should say mercury atoms touching the glass adhere to the walls less than to each other, forming a convex surface, right? In a test tube like that, you do get a meniscus with mercury. Here's water, but it just is the opposite way. You don't actually see this much anymore, but if you go to the doctor's office and they take your blood pressure with an actual mercury, it's not called a barometer, it begins with an S, but a blood pressure machine with mercury in it, you will notice that convex meniscus there. And then this is the final picture of this short little section. This is capillary action. This is a lot of words, okay? The process by which a liquid rises in a tube because of a combination of adhesion to the walls of the tube and cohesion between the liquid particles. Whew, that's a mouthful. Okay, so let's start this off. The process by which a liquid rises in a tube A liquid rises in a tube because of a combination of adhesion to the walls of the tube and cohesion between the liquid particles. This only happens in very small tubes, right? We know that a capillary, think of in biology, capillaries are those smallest blood vessels there. Capillary action is how water moves up a tree. If you think of how much water a tree absorbs in a day, it's gallons and gallons of water, and it has to move up to the leaves because that's where photosynthesis occurs. So the water really needs to move a great distance. And how does it do that? The tree does not use any energy moving that water up. It happens just naturally by the process of capillary action, where the water, this is a obviously an electron microscope picture of the water conducting cells within the structure of the cellulose of a tree. And look at the picture of the water molecules here, right? They are attracted to, that's not what I wanted. They are attracted to the walls of the container, and they sort of move their way up through both cohesion and adhesion. So there actually isn't a lot of homework to do from this section. I don't even know if this is a writing question or a multiple choice question, but it's just question number 22. You're going to get, a lot of practice in this because there's lots of places for CERs to come in here. So we're gonna deal with that a little bit later, but those are the properties of liquids, and we will look at the nature of solids in the next video.